So, we had for the 4 bar, we had the displacement equation in the form A cos theta 4 plus B sin theta 4 plus C equal to 0. Okay. So, where A, B, C are in terms of the known quantities, namely R1, R2, R3, R4 and theta 2. Remember, we are doing displacement analysis now. So, assuming you have designed a 4 bar, you have synthesized a 4 bar, you want to see how it is going to move. So, this is same sort of derivation as for Freudenstein's equation, except that the objective is different now. So, I can take the easiest way to simplify this is to substitute cos theta 4, you put it as 1 minus tan square theta 4 by 2 by 1 plus tan square theta 4 by 2, and then sin theta 4 similarly is 2 tan theta 4 by 2 by 1 plus tan square theta 4 by 2 in terms of the tan half angles. So, let me just, to make my life easier, let me say this is equal to T. So, I get, if I substitute back into this equation, I get A into 1 minus T square by 1 plus T square plus B 2 bt by 1 plus T square plus C equal to 0. Which becomes A into 1 minus T square plus 2 bt plus C into 1 plus T square equal to 0. If I group the terms, I will get C minus A into T square plus 2 bt plus A plus C equal to 0. This is nothing but a quadratic equation in T. So, T is minus B plus or minus. So, there will be a 2B, it will get cancelled. So, I will get, if I simplify this, 4B square minus 4 into C square minus A square by 2 into C minus A, which will simplify to minus B plus or minus square root of, I take out the 4 there, B square minus C square plus A square by, and theta 4, once you find T, you will get 2 roots of T. Theta 4 will be 2 tan inverse of T equal to pi, in that range. So, the plus and minus, the 2 roots of T correspond to, the plus and minus correspond to the 2 assembly modes or configurations of the linkage. What that means is, for a particular angle theta 2, theta 4 and another value theta 4 dash. So, theta 2 remains the same, but this will be the second assembly mode. So, I have OA, A, B, OB, OAA, B dash, OB. Those will be the two assembly modes for the linkage, right, and theta 3 you can find from one of the earlier equations, right. You had where you eliminated theta 3, you go back to that, plug in the value, two values of theta 4. So, you will get two values of theta 3 which correspond to. So, for this assembly mode you will get this, then for the second one this will be theta 3 dash. So, you will get a theta 3 theta 4 and a theta 3 dash theta 4 dash corresponding to the two assembly modes of the linkage. Okay. So, this is how you do the displacement analysis using the loop closure equation, which you may have seen before. Okay. So, what happens if, so we saw that we had a quadratic equation and the discriminant, right. If this is negative, b square minus c square plus a square is negative, then what does that mean? What does it mean physically? What are a, b and c functions of? The link lengths and the initial angle. So, if the discriminant is negative, it is possible that the linkage cannot be assembled in that particular configuration. Maybe it cannot be assembled for any value of theta 2. It could be just for a specific. So, if it is for specific values, then it may be that in a non-Grashof it is outside the range of, so it is past a toggle position in a non-Grashof. Otherwise, it is possible that for that set of link lengths you cannot form a linkage. Okay. So, that is what this means. So, the mechanism cannot be assembled in the specified position maybe because, one, it could be that the link lengths are incapable of assembly in any position or in a non-Grashof or a Grashof type 2, the input angle may be beyond a toggle position or a limit position. Okay, here the theta 3 from the previous equation you get as tan inverse r1 sin theta 1 plus r4 sin theta 4 minus r2 sin theta 2 divided by so where S theta 2 means sin theta 2, just a short form. So, now suppose I want to find the position of some specific point. So, if I was solving a path generation problem, right, I would want to know whether my point is hitting those specific positions, or even in a motion generation problem I want the position and the orientation of the so if I want to find, so it could, if I am looking at say a point on this, so this could be part of this link, this could be part of this link. So, I may be interested in finding the positions of specific points on various parts of the mechanism. So, if I call this I can, it is part of this rigid body. So, let us say I call this distance S, this distance Q, this distance P, small p, and it is easier for me because they are all part of, each one is part of a specific rigid body. It is easier for me to define their location in terms of a known. So, this I could call it delta 2 or delta S to be specific. So, S is, then I can call this delta P, and I could say with respect to. So, now this is my R1, R2, so they should form a closed loop, right. So, I have R4 and R3. So, I have R2 plus R3, that was my loop closure. So, once I have done the position analysis or the displacement analysis, okay, I know for every configuration I know the relationship between theta 2 and theta 4. It is not always necessary that theta 2 should be the input angle, okay, it could be theta 3 and your output could be theta 4, that is also possible, or you know in some, it really depends on the application. Typically theta 2 is your input, theta 4 is your output. So, here once I do the position analysis for this, you know, the kinematic chain, I can find the position of any point on the linkage. So, why do I say that once I find theta 4, okay, I can basically specify the location of any point on the linkage. Okay. So, here if I want RS, okay, RS is basically S e power I theta 2 plus delta S. Okay. So, any point on the input link, very straightforward. Once I know theta 2, once I know, I can find, and I know the distance of the point from the origin, and I can find that. Similarly, RQ is R1 plus q e power I theta 4 plus delta q. So, any point on the rocker can be determined in this fashion, because I know r1 and depending on the distance from OB I can find and the orientation of this of the line connecting OB to that point I can find this. Any point on the coupler, which is usually what we may be interested in. So, if I have an RP, it is R2 plus P e power I theta 3 plus delta P. So, where theta 3 is this angle. So, once you do the position analysis for the R1, R2, R3, R4, any point on the linkage is completely determined, okay, because S and delta S will not change. P and delta P will not change even as the linkage moves. It is relative to that rigid body, and P is a point on the rigid body, the coupler. So, with respect to any line on the coupler, its or any point on the coupler, its position does not change. Okay. So, this is how you find the location of. So, this is R2 e power I theta 2 plus P e power I of theta 3 plus delta P. So, now if you have synthesized a mechanism for path generation, you can use these equations after you synthesize to analyze and make sure it hits the points that you were intending to hit. Okay. So, that is now you can do the same thing. I will not do the whole thing, but I will just show you how to set up the loop closure equations for a slider crank. Okay. So, if I have so, let us take the general case of an offset slider crank, where there is an offset between the location of the fixed pivot and the path of motion of the slider. So, this is the offset slider crank. What you do for the slider crank is you choose the vectors. You could choose R2, R3 and take R1 from this pivot to this pivot OB, but that is not very useful, because what happens to R if I take that as say R1, its magnitude is going to change, the angle is also going to change. So, they are coupled together. Okay. So, it will make my life a little harder. So, what I will do is I will choose. So, I know that the slider block motion only happens along the direction R1. So, I choose one vector parallel to the direction of motion of the slider block and another vector perpendicular to it, because if you look at this vector R4 basically specifies the offset of the slider crank, therefore, it is not going to change as the mechanism moves. Okay, so, I am adding one more vector than necessary, but it is a constant vector. So, now I can write my loop closure equation as R2 plus R3 equal to R1 plus R4. In complex form, e power I theta 3 equal to r1 e power I theta 1 plus r4 e power I theta 4. Now, theta 1. So, I can always choose my axis such that theta 1 is 0, right. I choose it parallel to the path. So, theta 1 equal to 0 and theta 4 I always choose it perpendicular to that path. So, theta 4 is 90 degrees. So, this just becomes r1 plus I r4. Okay. Now, what are the knowns and unknowns in this equation? Again, it is a vector equation. Okay. So, the knowns, so you will be able to solve it for two unknowns. The knowns here are the link lengths R2, R3 and R4. The case of the 4 bar, all 4 link lengths were known. Here R1 is going to be varying. Okay. So, you have the R2, R3, R4 and your input angle theta 2. This will be your input. Okay. And if that is your input, sometimes the slider block could be the motion of the slider block could be the input, in which case R1 is your input. What are your unknowns? What else is known here? Unknowns are theta 3, R1, there is one more left, where do I put that? Theta 4 is known, right. So, theta 4 is known here. I already took it, but so you are essentially solving for theta 3 and R1. So, theta 3, if I take my vectors like this, this is the angle theta 3. So, again you would, I am not going to do it, you would separate it into the real and imaginary parts and you can solve for theta 3 and R1 to do this. Similarly, if you want to synthesize, then say you are given inputs R1 corresponding to theta 2 for multiple positions. Then similar to Freudenstein's equation that you did for theta 2 and theta 4, here theta 2 and your slider translation would be the inputs and you would try to find the link lengths to achieve that particular input. So, for analytical synthesis you would use a form similar to Freudenstein's equation for the 4 bar. So, that is one of your tutorial problems. So, I will leave you to do that. Okay. Moving on, we will go to the standard diode or standard form. So, using the complex number technique, so these methods that we used were mostly algebraic methods which use the complex number form of the vector loop equation, but there is a more general technique called using what is known as the diode or the standard form equation. So, if you look at a general 4 bar, I can actually look at it as formed by two diodes. So, I can say I have two links like that. okay, such that with the condition that this is like this. So, I could actually connect. So, I take two diodes and basically connect these two with a rigid rod, then I would form a 4 bar, right. So, this is sort of what we will use to develop this diode or standard form. So, so basically this says that you can synthesize a 4 bar in terms of these diodes. A diode is basically 2 links. Okay. So, what we will do is basically synthesize this 4 bar in terms of these 2 links. So, let me say that I have a 4 bar okay. I will call this vector W and this vector as Z, and I will call this vector as W star and this vector as Z star. A, B. Okay, and I have a coordinate system in which this is defined as R1 in position 1. So, this is point P in position 1. And let us say I give a certain input and this diode moves to, I will just look at this diode first and then I will say that this moves to by an angle beta j and the point P moves to this position P j. Okay. So, this is the angle. So, these two lines are parallel. Okay. So, this vector Z has rotated by gamma j. If this is gamma j, this is the original position, this is the original definition of that vector. I have rotated it by gamma j. So, this is Z e power I gamma j. So, what is this vector in terms of W? W e power I beta j. I have W which has moved to, and this here is my vector R j. Okay. So, here this is a 4 bar linkage with the left side represented by the vector pair W and Z, right side W star and Z star. So, once I know the two pairs, once W Z, W star, Z star are known, coupler AB and ground OA OB are known by vector addition. I can find it from the loop closure. So, all vector rotations are measured from the starting position, positive counterclockwise. So, here for instance beta 2 is the rotation of vector W from initial position to position 2, and so on. Beta j is rotation of vector W from initial position to position j. Similarly, gamma j is the rotation of the other vector from initial position to position j. So, let us say I want to write the loop closure equation for this. Okay. If I look at this, I can write this as W e power I beta j, okay, starting from here. Okay. One more thing. So, if I take R1 and Rj, what is this vector? Let me call this delta j. Okay. So, first let me write the loop closure and then we will. So, W e power I beta j plus Z e power I gamma j minus R j, because I am going this way. Okay. So, this is this minus R j, okay, then plus R1, okay, minus Z minus W. If I traverse this path, I come back to the starting position. I am back where I started. Okay. So, I can now write this as W e power I beta j minus 1 plus Z e power I gamma j minus 1 is equal to Rj minus R1, which is equal to delta J. So, what is delta J? Delta J is the displacement vector of some prescribed trajectory of the point P. Okay. So, this form of the equation, this W e power I beta j minus 1 plus e power gamma j minus 1 equal to delta j, this equation is called the standard form equation, standard or diode form equation. Okay. The next class we will see how we can use this to construct 4 bars and synthesize 4 bars, given for different types of functions also, different types of tasks, motion, path, function generation, etc. Because I am defining the vector, because see for the point P, the location of the point P, those are not so if I define, if I say that the linkage has to hit those points for instance, then I am giving you the positions of those points in my coordinate system. I am giving you, those are not changing. So, here I am looking at, so I am moving this diode from one position to another and trying to define this in terms of the movements of the diodes, the angular movements of the diodes. R1 to Rj are specified vectors. Okay, they will also have an angle, they will have a magnitude and an angle, but for this purpose you know the vector completely. What you are going to do with this is to actually synthesize. So, knowing beta j and gamma j, for instance, you will want to find out what should be W and Z to hit these points defined by R1 and Rj. Okay, then we will also look at function generation, you know, for W and Z with certain angles, W star, Z star, what the angle should be, so that you can do the synthesis of your linkage. Similarly, for motion generation, we will look at, because this displacement vector will be given. This basically shows the displacement of the point P1 to the position Pj. Okay. And the other thing that you will be given is, so when you are talking about motion generation, you will also be given the orientation of the coupler. You will be given the location of a point and the orientation of the coupler. So, there you will be given delta j and gamma j, you will be given the orientation of the coupler. Then you have to synthesize a linkage. So, we will see all those different forms as we go along. Okay, but this is called the diode or the standard form. It is a very elegant method for synthesizing 4 bar linkages.